So just as a plug, this technology is wonderful. I love how it's always able to follow me. Okay. So now let's talk a little bit about the integral from last time. So we had to look at the integral from 2 to x of du over log squared of u. And so when we're trying to understand how big could something like this be, it's natural to split it into different regions. And so we can do things a little bit more generally right now. Let's write the integral from 2 to x as the integral from 2 to f of x plus the integral from f of x to x. And let's try to get a sense of where we should choose for the split. So again, when we look at this, the question is what's going on? Well, as u gets very large, log squared of u is going to start to get bigger and bigger and bigger, so the integrand is going to get smaller. The difficulty is that we're integrating this over a very large range. So even though the integrand is getting small, it's traveling over such a large range that unfortunately it can still contribute significantly. And in fact, most of the contribution is not going to be where the log squared of u is small, but where the log squared of u is large. Now the other thing, of course, is the log squared of u. This is a very slowly growing function. So if you go from x halves to x, really order of magnitude, there's not much of a change. Look at the log of x squared versus the log of x halves squared. This is the log of x plus the log of 2, which is the log of x squared plus the 2 log 2 log x plus log 2 squared. It's the log of x squared plus essentially some constant of size 1 over log. Let's do it this way. Log of x. So if you look at the size of this term over here, yes?
Shouldn't that be a minus? Since you're dividing by it?
Oh, yes, it should be minus. Thank you. Yeah, thank you. I don't really care about, you're right, I don't care about this number here, I care about this number here, but you're right, it is a minus. Normally I go from x to 2x, but here, since we're integrating up to x, I did not want to go up to that. So when you look over here, this whole region going from x halves to x, the change in magnitude of log squared of u in that region is on the order of square root of the main term. It's essentially constant. And so that's the difficulty in things like this, is it's constant on very large regions. What if we replace the 2 with x to the c? Well, if we replace 2 with x to the c, then this becomes x to the c. Well, a better way to start doing the analysis is now this is the log of x to the 1 minus c squared, right? So I get a 1 minus c squared log of x squared. So there's now a constant decrease. So it's noticeably smaller. If your financial portfolio takes a 50% hit, you feel that, right? But it's still order of magnitude, it's still the same order, it's still log squared. So in terms of the contribution, it's still going to be contributing significantly. Now the amazing thing here is we're going from now not just x to x halves, but from x all the way down to a power savings. That is enormous in terms of how much we're moving. So if you think about the interval, here's 1, here's x to the, for the definiteness, here's x to the 1/3, here's x. If x is large, is this even remotely drawn to scale? No. This is maybe closer to 1/3 x. Maybe I should move this one a little bit further if I wanted to do that. X to the 1/3 is somewhere down there. And as x gets larger and larger and larger, this gets closer and closer and closer. We're looking at a very negligible amount of the integrand. So now, using arguments like this, if we want to try to figure out how big is this integral, well, let's see what we get. What we would get now is the first piece, the integral from 2 to f of x of 1 over log squared of u. Well, that's less than or equal to the length of the interval, f of x. And then we multiply by the largest value. And what's the largest value? So what would be, I'm sorry? 1 over log squared of 2. All right. Now let's look at the other piece. So now we have the integral from f of x to x of log squared of u. And so here I'll do the upper bound. The lower bound is similar. The upper bound will be x minus f of x, the length, times what? One over, not log squared x, log squared f of x. Because here I need to do the lower bound. So I need the log squared of f of x. It would be greater than or equal to x minus f of x times 1 over log squared of x. And if we choose f appropriately so that these are essentially the same size, these are going to be extremely close to each other. X minus f of x, about how big is that going to be? Well, we haven't said what f is, right? So this is the whole point, is you get freedom to choose f. If f is something like x over 2, well, then this is significant. This goes from being x to being of size x halves. But if f of x is growing slower than x, then you've got a big savings here. And so over here, we want to make this term smaller. We believe that this is going to be of size x over log squared of x. So this gives you some idea of what we should choose for f of x. We don't want to take f of x larger than what? So let's say we believe this integral is of size x over log squared of x. That's our belief. We believe the integral is that big. What would be a bad choice for f of x? And don't say x squared. It's too early in the morning for that. What would be a bad choice for f of x?
Log 2 squared over log squared x all times x.
All right, so basically some constant times x over log x. If you choose f to be x over log x up to a constant, I don't care about the log squared, 2 over here, that's insignificant. If f of x is of size x over log x, this is going to be larger than our predicted value. That means this is going to be a terrible estimation. In order for this to work, I need this estimate to be smaller than the expected main term. And I want most of the contribution to be coming from here. I want these two things to be sandwiched. So this is how you figure out what's the right order to take things. So we can see, we want f of x has to be little o of x over log squared of x. And so what little o means is if you take this and divide by this, in the limit you get 0. So this means f of x is going slower than x over log squared of x. Now it may be going slower by a very small amount. It may be losing by like a log x. But it is losing. If it's not losing, then this piece is going to either be of the same size or larger. But as long as f is going slower than that, then this piece will be an error term. Now, when you're doing problems like this, the difficulty is always how good of an estimate do you want? Are you just trying to get the main term? Are you trying to get the main term and an error term? And depending on what you're trying to do, you will make different cuts. Well, here, if I just want the main term as x over log squared of x, and I don't care so much about the error, do I want to take f of x to be close to x over log squared x, or do I want to take it far from x over log squared x? Close. The closer it is, the less variation there's going to be in this interval over here. That's where most of the contribution is coming. I want to keep x and f of x close. If they're close, log squared u varies so little that this upper and lower bounds, these estimates are going to be terrific. They're going to be very close to each other. It's going to sandwich the true value. So the larger f of x is, the better I can understand this integral. Because again, the difficulty is I don't know the antiderivative of 1 over log squared. The reason I don't know the antiderivative is there is no simple antiderivative of 1 over log squared. And that's why we're stuck doing something like this to try to estimate. So I want f of x to be large. Now, unfortunately, the larger f of x is, the worse my estimate's going to be over here. I would then maybe try to improve this. Maybe I would do some kind of dyadic decomposition. If f of x is large, maybe break this up into lots of different things. And so that might be a much better way of attacking this problem. Break it up into integrating from x halves to x fourths to x halves, x eighths to x fourths, and on each one of them, use very little fluctuation. But a lot of times that's more work than you need. And if you only care about the main term, you don't need to go through all those arguments. So looking at this now, this term over here will be insignificant. So let's say we choose f of x to be a little bit smaller than this. Let's just say for definiteness, we choose f of x equals x over log of x. What should I choose? I need a choice. I want f of x to be smaller than this. Give me a choice. This isn't hard. Give me a function that's smaller than this. OK. You want me to put an x to the alpha up top? I want it to be close to this, though. I want to lose. But I don't want to lose by too much. I want to be smaller than this, but I don't want to be enormously smaller.
Divide the little o expression by log x.
So divide this by log of x.
Yeah.
So what would I have down here? X over
Log squared x and then log x.
OK, so like log cubed x would be one possibility.
Yeah.
Right? Or if you want to be a little bit safe, you could even put a c over here and just say c is greater than 2. And if you do something like that, then you still have a free parameter to play with. It's often nice to have free parameters to play with. And so now when we do something like this, the log of f of x squared, what would that be? That would be the log of x minus the log. So we'd get a c outside. So minus c log of x squared. So it's going to be the log of x squared minus some constant of size log x over log x. Because the cross term is going to give me a log x, log x. Oh, sorry, here, I'm sorry. If I'm going to write it like this, I need to pull out a 1. So sorry. It would be of size log of x squared 1 plus constant log x over log of x. This is a good way to write it. And when I write it like this, I'm pulling out the main term, the log squared. I have a 1, and then here's my small little correction. So this is very, very small. Now here's the interesting thing. How much does c really matter here? If I did it log x cubed, log x to the 4th, log x to the 5th, does it really change things that much? Yeah, I can put like a little subscript c to remind myself the constant depends on c, but it's not going to change things greatly. If I allowed c to grow with x, then that would be different. I could have maybe c is 2 plus log x. If I really need to gain just a little bit of a small boost, I could try something like that. But when I do it here, we can see the log of f of x is so close to the log of x. The error here is very, very small. When I look at x minus f of x, this is going to essentially be of size x. So my upper bound is going to look like x times 1 over log squared f of x. Well, that's essentially, this piece over here is essentially going to be now x over log squared of x. And now I have to take the geometric series. I have 1 over this. So I would get 1 plus big OC of log x over log x. Just when I expand it out using the geometric series. And we see that that is a lower order term. The main term is x over log squared of x. The next term is going to be of size log x over log x. It's smaller. It's not smaller by a whole power of log x, but it is smaller. On the bottom one over here, this is much easier. Right? This is essentially just x over log squared x, what we want already. And then to do a little bit better job, we should say, well, but we also have the error of the f of x times this. Well, the f of x is x over log squared, so we can get really tight bounds. And we would get that this is equal to x over log squared of x, and we could even say plus or minus something of size and write it down explicitly. It looks like it would be of size x over log squared x, log x over log x. But this is how you handle problems like this. And this is how you try to figure out where do you want to split. Yes?
I was just wondering, once you find a bound, could you recursively use it for that first part, the 2 to f of x?
So we could do that as well. And again, the main contribution there is going to be coming from the end. And so if we plugged that in here, we would then get basically f of x over log squared f of x. And that would give us a little bit of a savings. And then that would lower this thing down a little bit more, yes. And so we're leaving a lot on the table by doing the analysis like this. And it's not surprising that we're leaving a lot on the table because, look, when you go from 2 to f of x, that's too wide of a version. So rather than splitting this up into one cut, what might we want to do? So one was this dyadic interval and doing a huge number of cuts. But what else could we do? So somewhere between 1 and many? 2 cuts, right? Maybe go from 2 to square root of x, and then square root of x to f of x, and then f of x to x. The other thing is to see, well, what if we chose f of x to be square root of x? What are we getting? How much are we missing? Well, if we choose square root of x, the errors over here are a little bit different, and you can go through and you can just propagate and see, is it really worthwhile? So it's a good exercise. I would suggest choose f of x equals square root of x, choose f of x equals this, and just write it all down very carefully and see what you get. All right, so now we've done splitting a sum, we've done splitting an integral. These are extremely important techniques because in general, sadly, we can't evaluate things. Okay, any questions about this?
Is it ever handy to go from 2 to f of x and then from f of x to f of x?
There are probably problems like that where you're having incredibly massive movement, almost sort of like an exponential cutting. So going from x to square root of x to 4th root of x to 8th root of x, depending on how your function is varying. And with a logarithmic dependence over here, that might make more sense. It really comes down to how good of an estimate do you need. For a lot of these problems, we don't need that good of an estimate, so it's not really worth going into too much detail. Okay, so now it's time to finally start the Riemann zeta function and L functions. Okay, out of curiosity, how many of you have seen the Riemann zeta function in a class before? In a class? What class? Complex analysis with me, okay, yes. So Riemann zeta function. So zeta of s is defined as the sum and goes from 1 to infinity of 1 over n to the s. And it is equal to a product p is prime 1 minus p to the minus s inverse. At least if the real part of s is greater than 1. And we write s as sigma plus it. As one of my advisors, Peter Sarnak, remarked, until you prove the Riemann hypothesis, you will use Riemann's notation. I think that is extremely good advice. Right? I don't know if I've talked in this class, I've talked in other classes this semester about how I want to change notation in mathematics, and I can find no traction. This one I'm not going to try. Why is this bad notation, sigma plus IT? Doesn't bother you at all? What are we doing? When did you first learn the letter T? How old were you? That long ago. When did you learn sigma? Fairly recently, right? Why did it take you so long? And I don't think you're exceptionally slow in this regard. Why did it take you so long to learn sigma? Greek is not our language, right? We're mixing two languages here, right? The real part we're using Greek, the imaginary part, Roman. English, whatever. Something other than Greek, non-Greek, right? It's mixed notation. This is the standard accepted notation. So the joke I always like to make is, this is 2014. Well, okay, I modified it a little bit based on the year. Can somebody give me the next integer after 2014? Next integer after that. Next one? You can keep doing this all day. All right, give me the next prime after 2014. Yes. So the distribution and the location of the primes is a lot more mysterious than the distribution and the location of integers. The integers have been extensively studied. Many things are known about integers, especially the spacings between adjacent integers. Okay? Exercise. Given n, next integer is n plus 1. Okay? Very well known. Okay? Because that is well known, the hope is that we can understand this sum here fairly well. And if we can understand this sum is linked to this product over primes. And the idea is then we should be able to pass from knowledge of the sum over integers to knowledge of the product over primes, and then somehow go back and forth. So the proof of this uses unique factorization, and it uses the geometric series. So those are the two ingredients. Why do you think we need the real part of S to be greater than 1? Well, it may diverge. So if I give you 1 over n to the s in absolute value, this is 1 over the absolute value of n to the sigma plus it. This is 1 over n to the sigma, and then this is 1 over e to the it log n. What's the absolute value of e to the it log n? 1. So if the real part is less than 1, we have a series who diverges absolutely. It may conditionally converge depending on t. For what value of t will it definitely diverge? 0. So if t equals 0, no hope in hell of converging, definitely going to diverge. For other values of t, maybe there's a chance that it could converge, that there could be some kind of cancellation. And it's not unreasonable to expect that there would be significant cancellation, because as n is getting large, this is wrapping around, you should expect some cancellation. But it's clear that we need the real part of S to be greater than 1. So one of the big things in the study of the Riemann zeta function is this notion of analytic continuation. You start with a function that makes sense only in one region, and then you extend it to a new function that makes sense elsewhere. So you might have seen the video 1 plus 2 plus 3 plus 4 plus 5. Does anybody know what this equals?
1/12.
Negative 1/12. Oh, come on. 1/12 is way too large for the sum of all positive numbers. I mean, why would the sum of all positive numbers be positive? So it overshoots infinity, comes back, and almost makes it to 0. What about the sum of the powers of 2? What does that equal? Oh, come on, this isn't that hard. Sum of all the powers of 2. I'll give you a hint. It's got to be less than the sum of the positive integers. No. No, you're close though. What? Multiply your answers. -1. Why is it -1? 1 over 1 minus 2. Use the geometric series formula, right? If you put on your engineering physics hats, right? Now, does the geometric series formula make sense here? No. But what you do have is 1 plus, I'll use x plus x squared plus x cubed plus ... equals 1 over 1 minus x if the absolute value of x is less than 1. So in this range, these two functions are equal. This function makes sense for all values of x other than 1. This function extends that function. We can use this to interpret 1 plus 2 plus 4 plus 8 plus 16. It is not the same as saying 1 plus 2 plus 4 plus 8 plus 16 is equal to -1. But in terms of an interpretation of what's going on, it's not horrible. How many of you have done anything periodically? It's okay, the camera can't see you, you can admit it. I've done a little bit. Periodically. So two-adically, this actually does make sense. And if you think about multiplying things, this really is the inverse of, it's related to the inverse of 2. Okay. So now, I'm sorry, this is not -1, I'm sorry. You were right when you said -1/2. No, it's negative. It's -1. Yeah, it can't be -1/2 because we don't have all the positive integers, so it's got to be smaller. So this is sadly not a course in complex analysis. There is complex analysis being offered in the spring here. It may be offered again next year. For those of you who can't take it this spring, I can't say advocate because that would be wrong for me to be saying that. Sorry. Okay. There is an advantage for not swiveling today. Okay. But there is some sections in the book which quickly go through some complex analysis. If you want me to go over complex analysis in the class, email me and let me know, and I will strongly consider doing that as a brief, 1 hour, 2 hour introduction to complex analysis. It's a good subject to know. It's good to know how to do stuff like that. So if a lot of you are not planning on taking complex either this year or next year, I will strongly consider that. All right, so the idea is we have functions that initially make sense in one region, and we come up with extensions that make sense in others. And it turns out that this is a useful thing to do because this function contains a lot of information. There's going to be a colloquium next week on special values of the Riemann zeta function. So I'm going to apologize in advance for stealing my colloquium students' thunder and doing some of the results right now. So let's go for it. What do you think would be a really good choice of s to take? I can study this function for any value of s. Give me a value of s. 2. All right. So we have the sum n goes from 1 to infinity of 1 over n squared. Using Fourier analysis, it turns out that this is pi squared over 6. And it turns out pi squared over 6 is an irrational number. So any idea how we might prove this? That the sum of 1 over n squared is pi squared over 6? The hint is Fourier analysis. What might be useful from Fourier analysis? Poisson summation is a possibility. What else? Dirichlet, that maybe if we evaluate a function at a special point, Bessel's equality, the sum of f hat of n squared is the L2 norm. Things like that can be used so that if the Fourier coefficients are nice, you can actually use that to get results like this. So there are ways to prove this using Fourier analysis. Now that we know this, this is called a special value proof. And this is not the politicized use of the word special where everything is special. Special value here means we are looking at a function at a very special point. By continuity, if I look at just the real part of s positive, Let's say I take the real part of s greater than 1. What happens is I crank up the value of s. What happens to this function? It gets smaller. It gets smaller continuously. So I can make this take on any value I want, that's no more than pi squared over 6. And as s goes to infinity, what value does it take? What does it converge to? Nope. 1. Because I've got the first term, I've got the 1. So I can make this take on any value essentially from 1 to positive infinity. So that's not really that interesting. What's interesting is where does it take specific values? So it's going to take, you want it to equal a value, fine. It's going to take on that value. But the fact that it takes on interesting values at interesting points, 1, 2, 3, the integers, these are nice numbers. The fact that you're getting a pi squared coming out. You might not expect to see a pi squared when you're summing 1 over n squared. And then, well, we're squaring, and pi comes in with squaring the, no. All right? It's amazing that you have a pi squared coming out. So here's the proof. If only finitely many primes, then zeta of 2 is rational. And the reason is if there's only finitely many primes, when I put in s of 2, I get 1 minus 1 over p squared. I get p squared minus 1 over p squared. Flip it, I get p squared over p squared minus 1. If there's only finitely many of them, a finite product of rational numbers is rational. What about an infinite product of rational numbers? Is an infinite product of rational numbers rational? Not necessarily. Can you give me an example of an infinite product of rationals that is not rational? Yeah, just point to the board, right? Here's an example of an infinite product of rationals that is not rational. This is a wonderful observation. Where have we seen a proof of the infinitude of primes? In class. Whose proof? Euclid's proof. So we didn't see the proof very long ago, but it's a proof from very long ago. Right? And in homage to the real part, it is it's a Greek proof. Right? Whose proof is better? Euclid's proof or this proof?
I think better overall,
In some fields, yes.
Better is strictly quantitative.
In this class, I can quantify. When my kids were little and I was asked, who do you love more? It's, who's sleeping better at night? That was the metric.
I actually really like the topological proof.
Furstenberg's? Furstenberg's proof is in the same category as this, and I would say it loses out to Euclid. I would say Euclid's proof is better than this. And I will defend that. Why do I prefer Euclid to this? One thing is it is partially constructive. You can use it to get to get primes, but related to that constructiveness, I'm sorry?
More intuitive.
It is an easier proof. It doesn't have the same level of sophistication, doesn't have the same depth of input. But it also gives you an estimate of how quickly the primes grow. This just uses the fact that if there are only finite many primes, there's a contradiction. So if anybody is still looking for a project to do for this class, I have an argument that quantifies this. Now, unfortunately, one of the things that I needed to use in the proof was the fact that there's a way to measure how irrational a number is. And I didn't realize when I was working this several years ago that one of the inputs used in quantifying how irrational pi squared over 6 is was the prime number theorem. So using the prime number theorem, that there are about x over log x primes at most x, I was able to prove that there are at least like little o of log x primes up to x, which you could do more directly by just looking at your assumptions. So what you then do is you then open up the proof of the irrationality of pi squared over 6 and see, okay, well, where the hell do I use the prime number theorem? What if I don't use the prime number theorem? What can I get? And it's amazing. You can get pretty far. I think one can get almost little o of x over log x primes infinitely often up to x. And so if anybody's still looking for a project, this would be a really good thing to look at. I've got a lot of notes on this, and just bring this to fruition, make this constructive. Okay? Any questions on this special value proof? So as long as we're here, do people want to talk about infinite products for a minute or two? Just build some intuition? All right. So we've just seen one. Infinite product of rationals can be irrational. What about the other one? Infinite product of rationals is rational. What do you think? If I have an infinite product, must it be irrational? Or can I, yes?
You just have all ones.
Okay. So we have the all ones. All right. So we have to give this a name. What should we call this?
One.
Trivial, boring, cheating, something along those lines. I'm sorry, what? Mathematics. So
Well, then is it trivial to say 1/2 times 2 times 1/3 times 3 times 1/4 times 4 times 1/5 times 5?
So we want all terms distinct. Okay, so now, I'm going to just keep shooting you guys down. Okay? So I want to shoot down David first, and then I'll shoot you down, okay? 2 times 1/2 times 3 times 1/3 times 4 times 1/4. It doesn't converge. So the problem is, if I look at things in pairs, it's fine. But it's going way up. So that is not an acceptable. All right, your turn, Blake.
Just like pick any epsilon that's less than 1,
Mhm.
and then just pick any arbitrary numbers in the interval negative epsilon to epsilon, multiply them all together, and they can all be different, and that would go to 0.
So we want product to converge to something non-zero. I told you I'd shoot you down. Because otherwise, again, it's too trivial. So we wanted the product to converge to something other than 0.
Did you center that I got something other than 0?
And now it's... Bless you.
I mean, you could do
What if I did this? That diverges. Now my numbers here are getting close to 1, but it's diverging. So this is not going to work, but it's not horrible. So what I need to do is I need something that's going to do a little bit better. So let's see if I try. So let me try this product. It's been a while since I've played these games. So if I take n equals 2, I get 2 times 2 over 1 times 3. What's the next term going to be?
3 times 3, 2 times 4.
And the next term is going to be 4 times 4 over 3 times 5, then 5 times 5 over 4 times 6. And so now if we see what goes on here, these 3 cancels with that, these 4s cancel with that, these 5s cancel with that. And what is this little number over here in the end going to become? It's going to go to 1. So what's this whole product going to go to? It's going to converge to 2. So here's a way to do it, okay? Now the difference here is rather than having something that looked like, n over n plus 1, I'm doing things with squares now. It's n squared over n squared minus 1. If you look at what's going on here, if I pull things down, I have basically 1 over 1 minus 1 over n squared. The other one was 1 over 1 minus 1 over n. It's the difference between a 1 over n and 1 over n squared. That's the convergence difference. So this is a way to get an infinite product that will converge to a rational number. And they'll all be rational terms. So it is doable. Okay? All right, so what this means is that if I tell you you've got an infinite product, you don't really know anything about its rationality, its algebraicity, its transcendentalness. It can be anything. And it's an interesting game to see how you can jerry-rig this. All right, so we took s equals 2. Can anybody think of another interesting choice of s? No. 3 is tough. So it turns out you can do 4. So it turns out whenever you take s to be an even integer, it's going to be that power of pi times a rational number. The odds are more mysterious and unknown. But there's an easier value of s that you're all missing. 1. Right? If you take s equals 1, the limit as s goes to 1 from above of zeta of s, what does that look like? It looks like the sum of 1 over n goes from 1 to infinity, which is infinity. If there were only finitely many primes, contradiction. Therefore, infinitely many primes, else the product is finite as s goes to 1. So this is a nice proof. And in fact, this gives you a lot more information. It gives you far more than just the infinitude of primes. I want to use this to very quickly show you that the sum of the reciprocals of the primes diverge and give you an estimate of how rapidly it diverges. So has everybody written this down because we're not swiveling today? Okay. So what I want to do is we don't have that much time, so I'm going to do things really fast, and I'm not going to make things too rigorous, which I like. So zeta x of s is going to be the sum, n less than or equal to x, of 1 over n to the s. And I claim that this is approximately the product over all primes less than or equal to x of 1 minus 1 over p to the s inverse. Okay? This is actually going to be, when we expand it out, this is going to contain a little bit more than this. Any number that's 1 over n to the s, all of its primes are clearly going to be less than x. When we expand it with the geometric series, we'll easily have them over here. But we'll have extra stuff here as well. That's fine. This will be a lower bound. And let's take s to be a real number. All right. What should I do? How should I understand this? What should I do? Logs. I almost bought a cowbell. If I could have found a cowbell when they were opening Western Fields, I would have bought it. There's a logarithm. If there's a logarithm, thou shalt take logs. Right? So zeta x of 1 is the sum n less than or equal to x of 1 over n. This is about the log of x. And this is about the product p less than or equal to x, 1 minus 1 over p inverse. So if I take logs, the log of zeta x of 1 is about log of x, which is about, now when I take the logs, the negative 1 comes out, I get negative sum p less than or equal to x of the log of 1 minus 1 over p. But what's the log of 1 minus u? It's minus u squared over 2 minus u cubed over 3. So this is approximately, the minus is reinforced, the sum p less than or equal to x of 1 over p. So here you go. The sum of the reciprocals of the primes is approximately log x. So not only do you get that there are so many primes that they're infinitely many, you get some idea of how rapidly they're growing. Now, of course, this is not quite right. I've got other terms, but the other terms that I'm dropping, they give a convergent thing. You can bound the rest with geometric series. bound rest with geometric series. You'll have a sum of 1 over k p to the k, p less than or equal to x, k goes from 2 to infinity. If I drop the k's here, I can use the geometric series. I can even extend the primes to being all the integers. And so as a nice exercise, bound the contribution from all this. It's going to be a finite number. Okay? So as a nice exercise, show that this contribution is finite, so the sum of 1 over p is looking like log x. Now the problem is, this includes a lot of other terms. This is more than just 1 over n. But it's a nice lower bound. So there's a lot that you can get just from the zeta function. All right, I will take a look and see if we have done enough stuff for the homework to still be due on Friday. And if there are some problems that we haven't done enough material yet to cover, I'll just move those to the next batch. Okay, any questions on zeta? So we will do the analytic continuation on Friday. And so there we will use Poisson summation. All right, so make sure you review that. We're finally going to use all that stuff. Okay.